Throughout this course, we're going to talk about learning and memory, but we're going to be using a lot of terms from a field of neuroscience. We're going to talk about how neurons communicate with each other and change because of learning. So it's important that we talk first about the nervous system a little bit, so that when I use this language in the future, you have some familiarity with things like how neurons communicate. So first, let's just talk about associative learning. There are two broad types of associative learning: classical conditioning and instrumental conditioning, sometimes called operant conditioning. The majority of this class is just about those two things. So I'm just introducing them now. We're going to talk a lot about them in the future. So in classical conditioning, two stimuli are brought together, two events are brought together in time, and we connect them. Animals connect them. And this is regardless of the animal's behavior. It's simply about recognizing that things happen together. So an animal is foraging, comes across a berry that's blue, and it associates the color blue and that type of bush with food. That's really important for survival. We're set up to make those associations. So in classical conditioning, two events are brought together in time and we connect them. We're going to talk about Pavlov. You may have heard of Ivan Pavlov. He rings a bell, he gives a dog food, he does that over and over again, and the bell becomes associated with food, so the bell makes the animal salivate. In instrumental conditioning, the outcome of the behavior is going to affect how the animal learns. So this is really a common way of learning. You might teach a dog to sit. You say the word sit, the animal sits, and you give them a liver doggy snacky yummy, and you praise them, a good dog, right? And if the animal doesn't sit, if your dog doesn't sit, you don't give them the praise, you don't give them the food. So there is a contingency between the behavior and the outcome. We don't see that contingency in classical conditioning. In classical conditioning, just bring two stimuli together in time. In instrumental conditioning, the outcome or another stimulus or reward is dependent on the animal's behavior. But it also could be punishment. Again, we're going to spend a whole bunch of lectures just talking about that, okay? So associations, connections are formed between two stimuli in classical conditioning. Sometimes a stimulus and a response. We'll get to that. And in instrumental conditioning, a connection or an association is created between a stimulus and behavior. The word sit becomes connected in the brain to the behavior of sitting. Again, we're going to spend a lot of time talking about that, but I thought I would introduce these concepts. Now, in associative learning, an animal has to have a synaptic nervous system. Most animals have synaptic nervous systems, from little flatworms over all the way to people and dolphins and rats and insects. They all have a synaptic nervous system, so they're all capable of classical conditioning and instrumental conditioning. So what is a synaptic nervous system? A synaptic nervous system is when the end of one neuron, the end of an axon of one neuron, sends a signal, a chemical signal, in the form of neurotransmitter, to the receptors of another neuron, the dendrite of another neuron, the cell body of another neuron, even another axon. And there's a space between the two where the neurotransmitter floats across. This is known as a synapse. Now, broader speaking, the central nervous system is the brain and the spinal cord, and the peripheral nervous system is outside of the brain and spinal cord, going to your fingers and to your toes and to your liver. This is known as the peripheral nervous system, and the peripheral nervous system is subdivided into the autonomic and the somatic. The autonomic, I think of autonomic as being automatic. We don't have a lot of control of the autonomic nervous system, but the somatic nervous system goes to the muscles. It also brings information from your skin and feelings, right? You have conscious awareness. A lot of associative learning takes place at both these levels. So the central nervous system is the brain and the spinal cord, and the neurons in that system are slightly different than the peripheral nervous system. Okay, the autonomic nervous system affects several areas of the body that we don't really have a lot of conscious control over. Your eyes dilate, whether you salivate, your heart rate, things like that. The autonomic nervous system is divided into the parasympathetic and sympathetic. Now, the sympathetic nervous system and the parasympathetic nervous system go to the same areas of the body. They just do different things. The sympathetic nervous system sometimes is called your fight or flight nervous system because it activates, it arouses your system, right? You're going to be attacked by a bear, your sympathetic nervous system kicks in, and you can get more blood to your muscles, your eyes dilate, your heart rate increases because you got to pump all that blood, your lungs open up so you get a lot of oxygen. The parasympathetic nervous system does just the opposite. It relaxes you. And it happens when you're not under threat. And this is when you can digest your food and your eyes don't have to bring in all this information so your pupils aren't dilated. And then finally, the somatic nervous system is you have conscious control over your muscles. So you can move your fingers and move your arms, but it also brings information from your sensory systems that you have conscious awareness of. So if somebody touches your hand, you can feel it. If something is gurgling in your stomach, you can feel the rumbling, right? So we're going to talk about how associative learning affects those nervous systems. Okay, so here's the neuron. You're probably familiar with this. Maybe you had a course in biopsychology. I'm sure you even had this in intro psych. A neuron is a cell in the brain. We have about 86 billion of them, and they make these connections with other neurons. And they're very unique in that they send signals, electrical and chemical signals. Now, there are other cells in the brain. These are glial cells, and they function to help with this signal. And the rate at which we send a signal tells us a lot about its effect on another neuron. So a neuron sends a signal, we call these action potentials. That signal travels down the axon and will then cause the influx of calcium. Calcium will then cause the release of neurotransmitters, which affect another cell. And all we have when it comes to the nervous system is how many times it sends a signal per second, which changes constantly. Maybe it's sending a signal 25 times per second. And then it gets information from other neurons to tell this neuron, speed up. Fire more times. We call this firing. Fire more times per second. Now it's firing 300 times per second. And then other neurons say, slow down. And telling this neuron to slow down. And now it's down to 150. Well, you have 86 billion neurons, each sending signals at different rates. That's really super complex. Okay. Now, those chemicals that are released are broadly divided into different classes depending on their action. So we could have a neurotransmitter that goes across and tells that other neuron, what I want you to do is fire at a higher rate. We call these excitatory neurotransmitters. So neuron is firing 100 times per second, then it gets a lot of excitatory neurotransmitters affecting the dendrites in the cell, and now it bumps up to 200, 300, 700 times per second. These are excitatory. So examples of excitatory neurotransmitters are things like glutamate, the most common, right? Dopamine can be excitatory. Norepinephrine can be excitatory. Epinephrine can be excitatory. Acetylcholine, there's a lot of excitatory neurotransmitters. But if there are excitatory neurotransmitters, there have to be neurotransmitters that tell the other neuron, slow down. Don't fire more times per second, fire fewer times per second. We call these inhibitory neurotransmitters. And so GABA is a very common inhibitory neurotransmitter. Serotonin, which is known as 5-HT, 5-hydroxytryptamine. Serotonin can be inhibitory under certain circumstances. Dopamine can be inhibitory under certain circumstances and excitatory under others. We have another neurotransmitter called substance P. There's a lot of neurotransmitters that are inhibitory. In this class, you don't need to know these, but you do need to know the broader idea that one neuron can tell another neuron fire more times per second, and one neuron can tell another neuron slow down, fire fewer times per second. We're going to use the idea of excitation and inhibition a lot when we talk about classical conditioning and instrumental conditioning. So here's a little neuron here, and it's sending a signal. And this neuron over here is telling this neuron fire more times per second. It's releasing a glutamate. And this neuron over here is sending a signal saying, slow down. Maybe it's using GABA. And the neuron, for lack of a better word, is kind of an accountant. It just says, how much excitation do I have? How much inhibition do I have? I will take both of those into account, and that will determine my firing rate, which will ultimately affect another neuron. Now, I only have one neuron here and one neuron here and one neuron sending a signal, but this is so much more complex. Recently, Harvard did some beautiful imaging of a neuron. So this is a single neuron. This blue neuron here is really this neuron here, right? It has an axon leaving it in white. But look at all the thousands and thousands of neuron signals that it's getting from other neurons. Look at all these connections. The white is the dendrite, but look at these signals coming in, excitatory, inhibitory. This is extremely complex. And these neurons are constantly changing. The dendrites are branching and the axons are branching, and we have more and more connections. We have what's called synaptogenesis. The creation of synapses are happening all the time. And when do they happen? They happen because of experience. They are representation of learning. Now, another thing we should learn about, because Pavlov talked a lot about this, is what's known as a reflex arc. A reflex arc is simply information comes in and information goes out in a reflex. So sensory information comes in, goes to the spinal cord. We have interneurons that could be excitatory interneurons, inhibitory interneurons, and then they go out in what are called motor neurons. These are sometimes called afferent and efferent. So here somebody gets a little touch on the finger, a receptor, a sensory receptor is sending a signal. We call this, it brings information to the central nervous system. These are known as afferent. Afferent neurons bring information to the central nervous system. These are sometimes called sensory neurons. Now, something happens at the spinal cord, but then information can go out. Now, let's say you're walking along and you're barefoot and you step on a pin or you step in fire or something. Don't step in fire, but let's say you do. We need to have a fast reaction. I mean, that information can go up the spinal cord into the brain. Your brain can go, hey, I believe you're on fire right now. But that takes some time. So we have the ability to feel that sensation and do something about it without having it go up to the brain to make a decision. We call this a reflex. We have lots of reflexes. So the sensory information comes in, goes to an interneuron, then comes out to what's a motor neuron, an efferent neuron, goes to a muscle. This can be really complex because it not only will pull your foot out of the fire, but it'll add strength to the muscles of the other leg, so it takes that weight, all at a reflexive level. Afferent, efferent, right? Sensory, motor. Okay, so we have these types of neurons. We have sensory neurons, we have sensory neurons that bring information to the central nervous system, and motor or efferent neurons that send information away from the central nervous system. Again, all this language is going to be used throughout this course, so we're just getting some familiarity with it. Now, neurons also change with experience, as I mentioned. We see we have some connections, and then we have some experiences, some learning, and we form new connections. Synaptogenesis. We form new connections, and we might even get rid of connections that aren't needed. This happens a lot during early childhood development. The neurons are modifying constantly, but they do it as adults too. So, dendrites are bringing information to the main cell. We call that the cell body or the soma. And these dendritic branches are constantly branching out and connecting with axons from other neurons. That's a really complex thing, but they're highly reactive to experience. When we learn, when we have experiences, we have these patterns of dendrites and axons that modify and change because of that experience to represent at the physiological level what's been learned. Okay, so finally we're going to end with something that we're not going to talk a lot about in this class, but we have to keep in mind. Just like we have to keep in mind all the biological and genetic factors that could influence learning, we need to take into account what's called non-associative learning. This is not where things are connected. These are simply changes that don't have to be represented by these connection synaptic changes. The first is habituation. This is simply a decline in response to a repeated exposure to a neutral stimulus or a stimulus or an experience that doesn't really have a lot of threat. I had a professor once talk about habituation. He says, an animal constantly evaluates the stimulation it's getting. And it says, if this stimulus, this event that it's experiencing, if it doesn't feed you, if it doesn't harm you, and if you can't have sex with it, we stop responding to it, right? And so sometimes we think about it as a loss of attention. Attention is something a little bit more complex. It's just simply a decline in a response to a stimulus that doesn't have a lot of relevance. We have the ability to do that. The opposite of habituation is what's called sensitization. Sensitization is an increase in a response because of an experience. Usually that experience is something noxious, something painful, something loud, right? So if something happens where an animal is hurt or threatened, it might be hyper reactive to any stimuli in the future, at least for the short time period, right? Habituation is a decline because of an experience. Sensitization is an increase. We're going to talk about both of these in class a little bit. So all animals show levels of non-associative learning. So here's an example. I kind of think of this one. So let's say you're over at Morro Bay and you're walking around the tide pools and you see a sea anemone. This is it's in the phylum Cnidaria. I don't know why I remember that, which is a relative of like jellyfish and things like that. Now, this has some sensory information. If you poke this, like you took a little stick and you poked it, you poke it right here, it's going to bring all its tentacles in. It's going to bring those tentacles in. But if you keep poking it every 20 seconds, you poke it, eventually, as long as the poke isn't painful or injury to this animal, it'll eventually stop bringing its tentacles in. It'll habituate to that sensation. We need to keep this in mind when we're doing experiments because not only do animals maybe associate things, but they habituate to others. We habituate to things all the time. If you have a fish tank in your house, and when you first get it, you really are attending to and you're hearing those fish bubbles, bubble, 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 right? The sounds. After a while, you stop really attending to it, and then you really aren't even processing that information anymore. Smells. This happens. We really habituate to smells often, right? You might move into a new apartment, and you go there and you go, boy, this apartment really has a smell to it, right? I don't know, the last people had cats or something. And you might find it not very pleasant, but after you live there a couple of weeks, you might say, hey, that smell is gone. Oh, that's great. But if you had friends come over for the first time, they're going to smell it because it's new, it's novel, and they're going to smell that smell. And you're going to like, well, it used to smell like, cat food in here and kitty litter, and it doesn't anymore. And they're like, yeah, no, it still does. We don't attend to it, but we also don't process those. If you wear a watch, you don't really notice that stimulation on your wrist. You put it on, you feel it, but eventually the skin sensory systems just stop responding, right? Sight, orientation, all those things we orient towards, all animals do, sort of new and novel things. Again, is this going to feed me? Is this going to hurt me? Can I have sex with it? If those aren't factors that are true, if it isn't relevant, then we begin to habituate to those things. Okay, I think we've done some background already. We have some language that we can talk about. Now we're going to move right into talking about theories of learning, and we're going to start with classical conditioning.